Welcome back, everybody. Another lecture this week about optimization and corner point. And in the previous couple of weeks, we've been looking at systems of linear equations and then systems of linear inequalities. And we saw that the inequalities needed to be graphed to be fully understood, and there were a whole bunch of solutions. We saw in linear equations where there could be many solutions, infinitely many solutions, but it was more of a special case than it was a general rule. For linear inequalities, systems of inequalities usually had many solutions. As a matter of fact, we made a whole big deal about shading those regions and then finding the region which was double shaded, triple shaded, all the different shadings. And so when all of those things combine, right, we will apply those to optimization problems. Right? The way that we apply them to optimization problems is we basically make our reality into inequalities. It's not that crazy when we do it, right? If you imagine I need to spend less than my budget, how much money I earn at my job. So if I made a variable out of all of the different choices that I make, right, the sum total cost of all of my choices needs to be less than my budget. And lots of things follow this reality, right? Maybe we want to schedule somebody at work, right? We'll see an example like that later. Maybe we want to build something, right? And we've got a certain number of pieces of wood to do it, right? We're always bound by some reality. And that reality can often be expressed using inequalities. Right? Certainly the kinds of methods that we'll learn in this class, only the kinds of realities that can be expressed as linear inequalities will work. But you'll find that it works for a lot more cases than it might otherwise seem. Right? Linear cases are actually very strong, right? And we don't have to stray that far from reality to make a linear situation work. I remember when I was in grad school, there were times in grad school we were still talking about linear equations in some seemingly very difficult classes. Right? And that was because the linear nature of it captured almost perfectly the reality of the situation. It can't be perfect, of course, but it gets you a lot farther than you think. Right? And so basically what we do is we model our choices by these inequalities, and then once we have a feasible region, that is the shading part of the solution to all the system of inequalities, then we will pick between all of those different possibilities using a couple of different methods that we'll learn this week and next. So our choice is constrained, and that constraint will be modeled by the inequalities. We will graph them this week. Like I said, next week we'll have more methods, but this week we'll stick to the graphical methods. And we'll very quickly turn even the graphical method into a non-graphical method. Here's a short example. A business decides how much time to assign one of its workers to office work versus field work. Maybe this is a biology lab. Right? And so you spend part of your time writing your reports and part of the time actually going out into the field to collect samples. Okay, maybe this is some other kind of sales job, right? Where you're working on your contracts behind the desk versus going out and meeting contacts out in the field. Right? Not that crazy of a reality. There are 40 hours in the work week. Right? Again, that number can be adjusted, maybe 50 hours, maybe 35 hours, right? But there are a finite number of hours in the work week. It certainly can't be any higher than, 7 times 24? 168 or so? Can't be any higher than 168. But whatever the total number of work week hours there are, that's a constraint. So I'm going to model this using a system of inequalities. Let me choose my choices to be the variables. In this case, this business is deciding between assigning work time in the office versus work time in the field. And so because those are two choices, let me make them my two variables. it doesn't matter which one is which, but I'm going to choose to make X the number of hours of office work that I'm doing, and Y to be the number of hours of field work that I'm doing. These things are always your choices. Right? My constraints, my inequalities that I'm about to start writing, model the things which I do not get to choose. Maybe I get to choose them indirectly. That is, my choices have to fall within a certain set of constraints. I can't really choose, right, what the constraints are. I can merely choose how I respond to those constraints. So in this case, in the word problem, it says that there are 40 hours in the work week. And so the total number of hours that I work has to be less than or equal to 40. Let me see how I would write that as an inequality. The total number of hours that I work, I think that is X plus Y. The total number of hours that I work has to be less than or equal to 40. Right? I agree with you that it seems a little silly. Why wouldn't this business assign all 40 hours worth of work? But that is a possibility. We'll see later on that having this sort of region, the interior region, doesn't make a whole lot of sense because it will never be optimal. Why would business leave hours on the table if they had them available? Right? But mathematically, I still have to consider all of the possibilities. X plus Y is less than or equal to 40. And so this is the work week constraint. You'll find that every time we have a constraint, right, we'll be able to write that constraint as an inequality. And I will go ahead and graph this constraint, X plus Y is less than or equal to 40. Let me see. I'm going to choose to graph my intercepts first. The intercepts here are 0, 40 and 40, 0. And I got those very quickly by plugging in 0 for one variable and finding the other variable. This line technically continues forever, but as we're about to see in a minute, when we do these kinds of application problems, we rarely will continue the line outside the first quadrant. The reason for that is because if I'm working some numbers of hours per week, I can't work a negative amount of hours. That doesn't make any sense. What does that mean? If I work a negative amount of hours, does that mean I need to give money back? Nothing about that makes sense. And so very often we will have what's called the reality constraints, right? That is, they're not inherently said in the problem, but they're implied by the fact that this is reality. I can't work less than 0 hours per week. So I need X to be greater than or equal to 0, and I need Y to be greater than or equal to 0. Most of the time, when I write these problems in the future, I will just write them both X, Y greater than or equal to 0. I don't need to see those every single time, even though they will show up in pretty much every application word problem we have. But for right now, this first example, I'm going to list them as two separate constraints. We saw the X is greater than or equal to 0 constraint last week in the graphing systems of linear inequalities problems. Right? We saw that that was one of the axes, and we wanted to shade in the positive direction. It's really hard to show that. I'm just going to have to make it a little bit thicker. Not too thick, though. I still want to be able to see that my line is there. 40. Oh, my graphing is awful today. Excuse me. And then the Y is greater than or equal to 0 constraint shows up as this, the x-axis. That's where Y equals 0. Remember, the first step of graphing all of these things is to graph the line, because the line is the equal to part. Now for the rest of these, I will consider the shading. Right, I've got shading in this direction, right, for the x equals 0 constraint. I've got shading in this direction for the y greater than 0 constraint. Okay, sorry about that. I reconnected my tablet. The shading that you see is the red shading arrows come from the x is greater than or equal to 0 constraint. That's the right side of my picture. The green shading arrows come from the y is greater than or equal to 0 constraint. And the blue shading arrows will come from the x plus y is less than or equal to 40 constraint. Remember, any line that's not one of the two axes, I often plug in 0, 0 just to see, do I shade towards 0, 0, the origin, or do I shade away from 0, 0, the origin? So if I've plugged in 0, 0, 0 plus 0 is certainly less than 40. So I will shade towards the origin. And which area is shaded in all three of the shadings? Well, that's this one area here, below the diagonal-ish line, but above or to the right, all of the axes. I've used a very, very faint highlighter here because if I use something too dark, like I do when I need to point and talk at the same time, you see how that would be too dark to see all the shading? I've used a very, very faint highlighter. And this region which I have shaded would be the solution to the system of inequalities. That shaded region. I did it in a squiggly arrow so you didn't confuse it with the shading arrows. The solution to the system of inequalities. I call that the feasible region. The reason I call that the feasible region is because all of the points in the shaded area are possible to choose. I could choose, let's just pick one random point here. This point, let me call it 15 and 20. It is possible to choose that point. 15 plus 20 is less than 40, as well as 15 is greater than 0 and 20 is greater than 0. I plugged in those numbers into all three of my constraints. So it is possible to choose it. I'm not sure it will be optimal, right? But then again, we haven't decided how do we choose between all of these possibilities anyway. Nothing about this so far helps me decide between all the possibilities. This is just graphing the system and shading the region, right? None of this helps me decide which one of those particular solutions that I should choose. And so there's my graphical system of inequalities. In particular, that feasible region that's shaded, that's what I'm going to focus on for the rest of today. Right? My optimal solution lies somewhere within that shaded region. So let's look at feasible region. You saw me do one in the example, right? But this is often the hardest part of these application problem. And the reason is no one tells you what it should look like. Right? When you look at a word problem, nothing in the word problem is going to say X is Y is Z. Right? Every now and again, you'll get a word problem which says let X be blank or let Y be blank. Right? But in general, no one tells you how many variables there are, and no one tells you what those variables should be. You have to make them up yourself. As a matter of fact, as we go forward with this, there might be 6 variables. I run out of letters very quickly. And so instead of calling those letters X, Y, and Z, I know I used X and Y because there were only two, right? When there are more of them, we'll start calling them just by numbers. X number 1, X number 2, X number 3. Right? That will look like X1, X2, and X3. That's what it will look like in the future. For this week, we'll try to stick with X and Y just because we're graphing in 2 dimensions only. But no one tells you how many there are even. Right? One of the things I like to tell students is every time you make a choice, that needs to be a variable. Right? And these are your direct choices. Remember up above when we were talking about the work week? Well, the work week was 40 hours long, and so that was kind of an indirect choice. For example, if I chose to work 30 hours in the office, I could not choose to also work 30 hours in the field. 30 plus 30 would be greater than 40. That's kind of an indirect choice. That's more of a constraint than a choice. The things I choose, office work and field work, those are variables. You can call them X and Y. You could call them X1, Y, or X1, X2. Okay? They are variables. The other thing which helps me form these things, these systems of inequalities, all of my constraints are the inequalities. And I like to model my constraints with inequalities because the method that we're going to start using requires inequalities. Remember earlier how I said that if I had 40 hours to spend, quote unquote, on assigning a worker, why would I ever choose less than 40 hours? Well, I don't know. Right? If there's only one constraint, then probably I wouldn't choose less than 40 hours to be the total work week. But if there were other constraints, that might change. Say, for example, that I was not allowed to work more than 15 hours in the field every week. Right? That would have been another constraint. Right? Going back to my example here, working 15 hours worth of field work as a max would have added y has to be less than or equal to 15 to my system. That would have added a new line to my system. It would have added a new shading to my consideration, and it would have changed the feasible region, which I got as a result. And so just because one constraint doesn't make a whole lot of sense to use as an inequality versus an equation, I can guarantee you that using equations is going to make the method harder to do. Right? It's actually easier to deal with inequalities than equations in the method. And so whenever possible, I'll try to write my inequalities in this form, right? All the variables on one side, less than a number on the right side. Maybe my contract says that I have to, I don't know, we'd have to get into, like, maybe it was something like I have to work at least twice as many office work hours as field work hours. In which case I would say, well, okay, well, office work hours and field work hours, right? So there has to be, oh, excuse me, got that backwards. There has to be twice as many, right? The 2 has to go on the other side than you think, right? Because if you remember, y is the smaller number, x would be the bigger number. So to make them equal, I have to multiply the y one times 2. This would tell me that the office hours has to be exactly twice as big as the fieldwork hours. Well, maybe that it's a less than constraint. Maybe the office hours has to be less than twice the fieldwork hours. And so there's a constraint. I would choose to write it like this, moving it to the other side of the inequality, because I like to see all of my variables on one side and all of my numbers on the other, right? You can see how we can model quite a lot of real-ish constraints with these inequalities. Right? That one is a little bit more goofy of an inequality, right? But usually these kinds of constraints will be because I'm limited to some budget. I'll write my total budget on one side and less than or equal to, right, the number, my budget, on the other. Or maybe I only have a certain number of hours to work, right, in a given department, right? I'll write the total number of hours on one side using variables, and then the number tells me the budget, right, the labor hour budget. Lots of different things will fall into that category. So all of my choices are variables. Excuse me. All of my constraints are inequalities. All constraints must be linear inequalities. That is, right, if I'm adding a certain number for every unit, right? I'm not allowed to say, well, okay, if I square the number of office hours, that has to be less than the total 3 times the number of fieldwork hours. Right? That's not a linear constraint. Right? As we see in a minute, right, everything about this method deals with linear constraints. But again, linear constraints aren't that big of an issue. Right? Most of my reality constraints, they can actually be modeled as linear constraints. I only mention here because I have to say, right, for the mathematician inside me, I have to say that these have to be linear inequalities. Okay, so these have to be linear constraints, and all the variables must be positive. Or 0. Right? I know I could have written that all variables must not be negative. And you see how not being negative is the same thing as being positive or being 0, right? But I prefer to write it out like that. So those guidelines help me make word problems out of, or make systems of inequalities out of word problems. Right? And because that's often going to be the hardest part of this process, I found that we're going to need to be doing this quite a bit. And so I like to keep these things in my back pocket. Once we have our inequalities formed, right, we call that solution the feasible region, just like we did earlier. And I'm allowed to make any choice, right, any solution inside that feasible region. Right? So I have to decide which one of those choices is the optimal choice, or does an optimal choice even exist at all? And that will be the next part of our class. Okay, sorry about that. I knocked out the charger from my tablet. Let's continue. The way that I choose between many solutions, right, the whole shaded region in my graph earlier, was to use an objective function. And this is not something that we had earlier, right? There are many different choices that I could make. And so to make this process easier, to make it possible at all, I need to be able to assign every possibility a number, right? I call it a score here in the text that I've already written, right? I basically give every possibility a score and choose the high score at the end. The way that I assign that score to every possibility is called an objective function. That objective function will contain the variables that I chose earlier. And so that's another way to help me decide, well, how many variables do I need, right? Generally in the problem, it tells you, well, if you want to maximize your profit, how do I calculate the profit? Right? I need to know the number of work hours for one and the number of work hours for the other. Right? Those two things are my variables. And so you can usually look to the word problem to kind of not cheat, but get insight into what the objective function should look like. That will help you decide the number of variables that you need, which are one of the most important decisions you need to make. How many variables do I need? So going back to that previous office work, fieldwork scenario, if the worker generates $100 an hour worth of profit in the office and $150 worth of profit every hour in the field, that tells me that my objective function can be written as follows. The amount of profit that I make, P, is equal to $100 times the number of hours that I work in the office. Right? You notice how X is the number of hours I work in the office. 100 would be the dollars per hour. So if you were to take this to town like a physics problem, dollars per hour times hours would equal a number of dollars. It would work out. And so sometimes when you see me return or give feedback on problems, I'll say the equation that you wrote doesn't make sense because the units don't match up. And what I mean when I say that is that here this is a dollars per hour, and this is a number of hours. So the hours would cancel out and leave me a measure of dollars. Profit is measured in dollars. It all works out. Plus, I'll do the same thing for field work. $150 per hour times the number of hours. And just like before, I could check to make sure this works. It's the same dollars per hour times hours. It's consistent. I can't tell you how often students will say, Professor, the part that's really hard for me is making the word problem in the first place. How do I choose the number of variables? How do I know what's a constraint and what's the objective function? How do I know which direction to put all of these things in? And that's the reason why I keep harping on it so much. It's because that's the part we'll have to practice the most, is making our word problem into a system of inequalities in the first place. I mean, once we have that objective function, notice how the objective function is an equation, not an inequality. If I were to put the objective function in the graph, it would be a perfectly straight line. It would not be shaded one direction or the other. 100x plus 150y is equal to a number. And so I would have to choose, right? Say p equals, right, 0, right? That would certainly go through the origin 0, 0. All of the possibilities where p equals 0 would fall onto a perfectly straight line. We're going to take advantage of that fact later on. Right? We're going to say, okay, well, if everything that has the same profit value falls on a line, let me just see where that line is. Or maybe I'll go to a different line. A different line would say, well, let me let my profit be $500. Okay. Certainly, I could have 1 point on that line, 50, 5 times 100 plus 150 times 0 would be 500, so it would fall on that line. But I could also have 2 times 100 plus 150 times 2, that's 300 plus 200. Yeah, that's also on this line. And let's see, did I put them in the correct? Looks like I didn't put them in the correct orientation on my line. 50 would be out here to the right. 2 would be closer to this side. Right? Again, I didn't draw any axes here, but if I drew my axes in the standard way, 5 should be on the lower right, 2 should be on the upper left. They are connected by a straight line, and every point on that line is the same profit value. The math geeks would call that an ISO profit line, but I won't require you to call it that. I will say ISO profit lines in the rest of this lecture and the rest of this video, but we won't need it too much outside the context of today, because most of the time when I say ISO profit line, I'm imagining that line anyway. I will rarely draw you an ISO profit line in the graph, right? We'll just use that as an idea that all of the things of the same profit value, the same objective function value, they fall on a straight line. So we won't need them too much outside of today, but I will refer to it as an ISO profit line, right? Geek squared ISO means equal. And so if you've ever heard of other words that begin with ISO, iso profit is one of them. How about isometric? Isometric, right, refers to, right, the equality of distances. When you have a certain camera angle, if you play video games, you might have said, oh, that's an isometric camera angle. ISO means equal. Okay, so we've got our feasible region, and we've got an objective function as a way to assign every point within that feasible region a score, right? And we want the high score, and we will call that the optimal point, or at least that is where P is the maximum value. Maybe if I had a different way to assign a score, maybe I wanted to do costs, and maybe I was doing costs instead of profits, and I want to minimize. Regardless, I'd still assign a score to every point and then pick the lowest score if I wanted to minimize my cost. So even though I have a way to choose between two different points, that doesn't give me a lot of insight yet, because remember, there are infinitely many points in this feasible region. I've drawn you just a generic feasible region here, and there are many points inside of it. I'm not going to pick every single point inside of it and assign every single point a score. So I need a way to narrow down this list. And for the rest of this video, I'm going to do something which looks remarkably like real math. And the interesting part about real math is people freak out when they hear that. And, oh no, my God, he's about to prove something, and he's about to break out, X's and yes, this will be very close to something we might call a proof, but I'm going to do it entirely geometrically. We don't need X's, and we don't need numbers, and we don't need lots of dense things to prove this. Right? I'm going to lay out my steps just like I've done here. My argument is that I want to only consider the corner points of this region. One of those corner points is either the optimal or the co-optimal, with a whole bunch of different ones. And so to do that, I need to eliminate some points from my region. Right? I'll make 4 arguments for you today. Argument number 1 says all of the points in the middle, right, which are in this shading region, I've made it in red. All of the points in the middle will never be optimal, and I will never need to consider them. Ever. Right? It's nice, right? It would be really nice if I could make that argument, because it would eliminate a lot of different points. In argument 2, I'll argue to you that if you're on the boundary, that doesn't mean that you're home free, right? The points on the boundary are never uniquely optimal. Right? And so moving in one direction or the other will either improve your situation, or at the very least will be exactly the same as what you started with. Right? So the points on the boundary will never be the uniquely optimal point. But argument number 3 says they may be co-optimal. Right? If moving in one direction or the other doesn't change your situation, right, they may be co-optimal. So argument 2 and 3 are very similar. And so points in the middle will never be optimal. Points on the edge will never be uniquely optimal, but they might be co-optimal. And so if I put all of those 3 things together, argument 4 will say, well, that must mean that I only need to look at the corner points, because no other point could be optimal or even co-optimal. Right? If I have that co-optimal situation, right, one of the corner points will always be co-optimal as well. Right? So let me throw all the other points away and look only at the corner point. And that would be a really nice argument to make, wouldn't it? Because how many corner points do you see in this feasible region? 1, 2, 3, 4, 5 corner points? It would be really nice to have 5 points to look at instead of infinitely many points to look at. That would make me really happy. So I'd like to narrow down this list. And here are my arguments. I've already half drawn them for you. My argument number one is that the interior points of the region are never optimal. And what I've done here is that I've picked one point. I know I've drawn the same argument twice. It's not two different points. I've picked one point in the middle of the region, right? If you remember the picture, right? This point would be somewhere in the middle of the region. And if it's in the middle of the region, I can draw a circle around that point small enough that it does not contain any of the boundaries, right? It doesn't matter how close to the edge I am. As long as I am truly in the middle and not on the edge, I will always be able to draw a circle small enough so that that circle does not contain any of the boundary points at all. And so that's basically what I've done here. The circles with the dotted lines around them, you see, that's the interior of the region, does not contain any of the boundary points. It's kind of a nice little trick, right? Because I can tell you, I can always draw this circle. That way I don't have to worry about the details of the particular numbers I'm dealing with. It doesn't matter, right? Everything inside this circle is inside the middle of the region. There are no boundaries anywhere. So let me just make this picture even simpler to deal with. Get rid of all of my marks here. Here we go. So this dotted line region is that imaginary circle in the interior of my region. Now, to prove to you that these points will never be optimal, I'm going to need that isoprofit line that we talked about earlier. Do you remember how the isoprofit line always connected together points which have the same profit value? Everything on the line would have had one particular profit value. Everything on one side of the line would have been greater than. Everything on the other side of the line would have been less than. Right? But the fact that those lines can always be drawn starting at any point in the region tells me I need to draw one of these isoprofit lines in my circle. Right? The nice part about the argument is that it doesn't matter how you draw your isoprofit line. Right? I'm going to draw my isoprofit line with a downward slope, but you don't have to. As a matter of fact, you should draw yours with an upward slope just to prove that to yourself that the argument I'm making doesn't depend on the way that I draw my isoprofit line. So this is my isoprofit line. Everything on this blue line has the same p-value as the middle of the circle. Okay? So how does that help me? Well, either the top side of the isoprofit line is better or the bottom side of the isoprofit line is better. And it can't be both, right? Remember when we were graphing our systems of inequalities, we would always start with the line that was the equal to, and then one side of the line or the other was better. Right? One side was greater than, one side was less than. Well, if this side is greater than, and I want the greater than, then do you see how half of this circle is better than what I'm currently looking at? Right? I'm currently standing at point P, and I'm looking out into the circle, and I'm saying, hey, anybody around here, is there anybody that's better than I am in the same little area circle that I'm looking at? Right? Well, it turns out there's lots of people which are better than me inside this circle, right? I've marked just one of them, but you can imagine that the same argument could be repeated for any of the points in this half circle, right? And so what this means is that there is a point which is better. There is a point which is better than P. That point is inside the circle, which means that it's inside the feasible region. And so if it's inside the feasible region, that means I could move there if I wanted to. So why don't I? It would improve my situation, and so P cannot be optimal. So if P is not optimal, that proves my argument. The interior point is not optimal. I'll leave it to you to pause for a moment. See, any way that you draw your isoprofit line, and any direction that you choose to be better, because remember, you could draw it with any slope going through here, and you could say any direction is better, right? Top side, bottom side, left side, right side. Any way that you draw your picture, there will always be another point that is better than P. So no matter how I draw the picture, it's the same. So I will call that a proof of argument number 1. No matter how I draw the picture, right? I've always got a P in the middle of the circle. I've always got the dotted circle around it. Right? There are no boundary points anywhere to be found. I can always draw an isoprofit line through the middle. It doesn't matter what slope I choose, though, and it doesn't matter which direction I choose to be better, right? Because no matter how I choose it, and no matter which direction is better, there are always exactly half the circle, which is better than P. Right? P is not optimal, and it doesn't matter how you draw it. I challenge you to find a way to draw this circle using the same rules. You won't be able to find a better point. Right? And it's an easy challenge to make because you can probably already see that you'll never be able to do it. And so argument number 1 is proven. Right? This might have been the very first time you've ever truly proved something in math. Now, this is not a formal proof in that sense, right? Because a formal proof would require, right, taking care of all of the details. But this is very, very close to a formal proof. Right? It's got all the elements of a proof, right? I've got everything I need. I showed all of the possibilities. I've shown you that no matter how you've drawn it, you'll never be able to find, right? Or excuse me, you'll always be able to find a point which is better. Right? That's dangerously close to a proof. Right? What I call quote unquote real math. Right? It wasn't as bad as it seemed, right? There were no numbers at all. All I had to do was draw a couple of lines to prove this to myself. So argument number 1, I will call proven. At least for this class, it's proven as much as we can prove it in this class. Interior points are never optimal. Okay? And so just like that, I've eliminated a great number of points from my region. Okay? So if it's not in the middle, it must be on the boundary. And so that's what argument 2 starts to consider. Boundary points are never uniquely optimal. That's the argument. The trick here is that boundary points, I don't know a whole lot about the boundary because now that these points are on the boundary, my circle diagrams, you see I've drawn 4 of them here, the circle diagrams will have to contain a boundary line, the boundary line that it's on, as well as, right, the isoprofit line. Right, so let me draw you a couple of different possibilities. And so let me say my boundary line goes in this direction. I will draw all of my boundaries in black. My boundary line goes in this direction, and my isoprofit line goes in this direction. In reality, they don't have to be so far apart. I've drawn this so that the angle between these two lines is pretty exaggerated. Right? They don't have to be that exaggerated. They might be in some cases, but to make these pictures easier to read and to make them easier to follow, I have chosen to draw them pretty exaggerated. So let's look. For the boundary line, now the boundary is not an inequality, remember? So the arrow that I draw on the boundary line doesn't represent which side is better. The arrow on the boundary line tells me, well, on the boundary, one side of the boundary is inside the feasible region and the other side is outside of it, right? The side of the boundary line, I'm just going to draw one particular direction here. The side of the boundary which is outside the feasible region can never be chosen, right? These things are outside the feasible region. I'm not allowed to move there at all. So I can eliminate everything in both of those regions, knowing that they are outside the boundary line. So one side of the boundary is inside, the other side is outside the feasible region. I've eliminated those outside the feasible region. Okay. Well, let me look at the isoprofit line now. I'm going to, again, choose, just for sake of argument, this direction. So isoprofit, and I've drawn the area which I'd like to move to. Everything in that direction is better. So is there a point in this circle which is better than point P? I think so. How about this one? You see how this point is better than point P? Now we know that that point is not optimal, right? According to argument 1, what we just finished doing, that point is never optimal because it's on the interior of the region. But that doesn't matter, right? My argument here is not, is that point the optimal point? My argument here is that the boundary point which I'm looking at is never the optimal point. That doesn't mean the interior point is the optimal point, but that does mean that it's currently better than what I'm looking at. And that's all I need here. And so that would be a counterexample. Right? So according to this diagram, point P is not optimal. Because this one that I've marked with a red X is better than P. Remember, that doesn't mean it's the optimal, that just means it's better than P. And I know what you're thinking, Professor Trevino, right? Now we're starting to get into the thick of it, right? Because now you've drawn two different lines in your circle. One of them is the boundary line, and I could have drawn that boundary line with any slope. And the other one is the isoprofit line, and I could have drawn that line with any slope. On top of that, I could have chose which side of the line is better, top side, bottom side. I know that one side is always better than the other. So I'm going to challenge you for a moment to see, well, can you draw a few of these on your own? See if you can ever come up with a situation where you don't come to the same conclusion. I'm going to draw in just a few examples which use roughly the same line slopes. But my line slopes will be the same, but I'm changing which side of which line I'm dealing with. So now you see the boundary line I'm shading in the opposite direction, but the isoprofit line is shaded in the same direction. Same scenario. I still get something which is better than P. Here the boundary line is on the top, but the isoprofit line is shaded down below. And I know it doesn't look like immediately right away, oh, hey, professor, those two aren't shaded. And there's no point where both of them are pointing. But remember that same arrow goes for both sides of the isoprofit line. So there is a point there. Right? Any point in this region is better than P. And one last diagram. Now this one is shaded here for the isoprofit line. No, shaded down below. And then the boundary line is shaded down below. You see how I've basically given you all four possibilities here? There's two ways to shade the boundary line and two ways to shade the isoprofit line. So there's four possibilities total. And I've given you all four possibilities. In all four of these shading possibilities, I can find a better point than point P. Right? But again, that's just how I've drawn these two particular lines. Maybe you want to try this on your own. You should try drawing a few of these boundary lines and isoprofit lines to see, well, if I drew them at a different angle to one another, would that help? Right? I don't think you would be able to find a particular angle which helps, because no matter which angle you have, half of the circle is always eliminated by the boundary line. The other half would be eliminated by the isoprofit line. Right? I didn't squiggle it out the same way I did the boundary line because they're not really eliminated. It's just I'm looking for better than what I have. I'll always be able to find that inside my circle. And remember, inside the circle, those are the things where the point which I'm currently standing, the point where I'm currently standing is a boundary point. You can see, right? If I zoomed out, this would be point P on the boundary, right? And I've drawn that circle around the boundary, which contains the isoprofit line. Sorry. So again, I'm not sort of going outside the bounds of reality here. I'm just zooming into my picture. Right? Just making it a little bit clearer by ignoring all of the unnecessary details. But I can still find a point which is better. And if I can find a point which is always better, this boundary point is never uniquely optimal. I can probably tell, right? Normally in class, I would lie at this point and I would say, I can see on your face that you have a serious misgiving. Right? And it's because you probably do, but I couldn't read it on your face. You're thinking, Professor, what if I drew these lines to be directly on top of one another? That's the only case which I didn't draw. And so I would be like, I would play the game, right? I would say, let's draw that situation where these two lines are directly on top of one another. So in this scenario, the boundary line and the isoprofit line are perfectly lined up, right? I know they don't look like they're on top of one another in my picture, but I needed to show you in the picture, right? The blue line and the black line, right? But in the graph, they would be perfectly on top of one another. Well, I could still draw the same argument I did before. I could eliminate half the picture because of the boundary line. But do you see that no matter which direction I draw the isoprofit, one side or the other side, let's see, if I drew it on this side, it wouldn't really be an issue, right? Because I'd have that point right there. So that point is, I'd say, the easy one. Let me copy this whole diagram. Oh, I don't need 2 copies of it. Sorry about that. Let's try this again. Let's not paste it twice. Here we go. I already know which one is the boundary and which one is the isoprofit. Now if I draw my isoprofit in this direction, do you see how there is no point that I could move to outside the feasible region, which is better than P? You would say, aha, I've disproven your argument, right? Because there is no point in this circle which is better than P. And unlike the one I drew on the left, right, there's no point better than P. you would say, that point is never purely optimal. But that's an argument 2 thing, right? Remember in argument 2, I said the boundary points are never uniquely optimal. Argument 3 says they may be co-optimal. And this is exactly the scenario we're looking at. Do you remember the isoprofit line, the blue line? It represents all of the points which have the exact same p-value, profit value. And so if they are all exactly the same, it's quite possible that they are all exactly optimal as well. Many optimal points might exist. Because the highlighter changes the colors, I need to write that back in there. Many points on this isoprofit line might be equal, and I will call them co-optimal. All of them would be equally optimal. And that could be a scenario. And so that's what argument 3 is telling you, right? So the boundary points will never be purely uniquely optimal, but they might be co-optimal. And so that's going to have to be an important caveat we're going to have to deal with later. It might be co-optimal. Still no numbers, right? By the way, we're almost done with this proof, quote unquote. Not a single number in sight. That's why I like this kind of math, is because it doesn't require an advanced degree to understand what's going on here. I'm just looking for a better point, one side or the other. Here's argument 4, where we kind of turn this around on its head. The argument here is that the optimal or co-optimal point must be at a corner point. And we have to be a little bit picky about the wording here. This is not saying that every corner point is an optimal or a co-optimal point. It's just saying that one of the corner points is either the optimal point or a co-optimal point. To do this, I think I don't even need the circle diagrams here. Let me erase my circle diagrams. I'm going to draw the zoomed out picture of the entire feasible region. Now the feasible region contains boundaries. I don't know exactly what they look like. I'm just going to draw you a weird one here. But we know that the feasible region has boundary points and corner points. So let me eliminate all of the points here except the corner points. So just like I did in the first diagram, the interior points were eliminated by argument 1. Can't be in the middle here. It will never be uniquely optimal, and the middle points won't be co-optimal either. Argument 2 said that all the boundary points, all the ones in between, these things are not allowed to be uniquely optimal. Right? The little asterisk on 3 says that, well, these may be co-optimal, but they're never going to be uniquely optimal. And so let's see what this looks like. So if it can never be in the middle, it has to be on the edge. I might stick a circle diagram, a half circle diagram in here. So if I have a corner point, there are 2 boundary lines in the corner point, and they don't go all the way through. You know what? Let me paste it. Sorry. Normally I don't do this with a circle diagram. Oh, not that circle diagram. I don't normally do this with a circle diagram. Pause, please. All right, welcome back. Sorry about that. I grabbed a circle diagram from up earlier. I don't normally draw a big circle diagram for the corner points, but I think it would actually help in this scenario. At the corner points, there are two boundary lines, and they don't go all the way through the circle. Right? They will have some angle between them. Right? So there are two boundary lines. And the isoprofit line will be exactly what a mathematician might call tangent. But in our terms, that would just mean it doesn't cut through the middle. Do you see how the boundary lines give me a region? This is roughly approximate to the corner point from up above. So it eliminates all of these regions because they're outside the feasible region. But the isoprofit line wants to go farther in that direction. I wouldn't have the isoprofit line going in the other direction because then, right, then all of those points would be better. One of these points will be this scenario. It will be the boundary, and it will be the isoprofit, and it will be exactly at a corner. The slope will be so that all of the points that are inside the boundary region are outside the isoprofit line's arrow, where it wants to go. This is the uniquely optimal point. Do you see how all of the points where I want to move to can't be moved to because they're outside the feasible region? One of the corner points will exhibit this behavior. And the nice part about this is that, again, if it's not this one, then it's one of the other ones. Right? I could make this drawing for all 5 of the 6 corner points. Excuse me, there are 6 corner points in this region. I could make this drawing, circle drawing, for all 6 of the corner points. Right? It will always work for one of them. So this is the unique optimal scenario. This one is uniquely optimal. But I'm still not going to forget about that circle diagram I had from before. Do you remember how in the circle diagram from before, I said, well, the corner points, or excuse me, the boundary points may be co-optimal? So if I have one of those scenarios where I have a boundary point which is co-optimal, here's what that would look like. I would have 2 boundary lines, and the isoprofit lines would overlap with one of the boundary lines. Doesn't matter which one, but one of the boundary lines, which means all of these points are co-optimal. But I could have exactly the same scenario at the corner point, which is connected to it, right? Let me imagine the corner point, which is farther up. Right? Do you see how I could just follow that boundary over to the next corner point? At the next corner point, there's the incoming boundary, and I don't know what the other boundary looks like, but I'll just say it's like this. And the isoprofit line is the same isoprofit line. And so I'll have the co-optimal situation at the other boundary point too. And so all of those points in between those 2 corner points, including the 2 corner points, are co-optimal. So there are 2 corner points which are co-optimal, and all the points between which are co-optimal. But it will always be that way. Right? When I have that co-optimal scenario, it will always be two of the corners and all of the points in between those two corners. And that's what I was saying earlier, where it could be a uniquely optimal point, or it could be a co-optimal point, in which case one of the corner points will have one of these properties. And so I think that proves argument number 4, right? That the corner points are the specialist points of all, right? One of the corner points is either uniquely optimal, or two of the corner points are co-optimal. And therefore, all of the points in between those corner points are also co-optimal. Right? And so all of this means, all of this is to say, right? Only the corner points are the ones we need to look at. Only the corner points are important. We don't need a big giant picture. We don't need to shade in, right? Once we've found the region, right? Give me the corner points of that region. You still need to do your shading to figure out which direction you're shading and where the corner points even are. But once you find those corner points, you can kind of throw your picture away, right? Later this week, when we do the second video, right, we will be talking about the corner points and we'll be making a list of them. And because we no longer need to look at any of the other points. Take a look at all the corners, plug them into your objective function. One of them will either be optimal or two of them will be co-optimal. Right? So I know that was a big heavy lift for today. This is probably the most dense topic of the entire class. And the reason I like talking about it is not because it's so dense, right? Mathematicians don't do our thing because we enjoy understanding things which are complicated. I think it's because this particular quote-unquote proof was not quite as complicated as you might expect a mathematical proof to be. You can go back and step through it, and I bet you can get it one step at a time. And there were no numbers, there were no equations, right? All that was required was we understood what the isoprofit lines were, and we kind of zoomed in selectively to different pieces of our graph. Right? Try it out on your own, right? Draw your own feasible region and draw your own isoprofit line. Just remember that if you're dealing with the same picture, right, for example, this last, right, once you draw your isoprofit line, then it needs to be the same isoprofit line in all your pictures. And I tried to draw the same one. I didn't get perfectly the right one in the uniquely optimal case, right? Because again, it depends on the isoprofit line. If the isoprofit line is perfectly aligned with one of the boundaries, then you'll have the co-optimal case. If the isoprofit line is not perfectly aligned with any of the boundaries, you'll have a uniquely optimal point. And so I couldn't draw the same line in both of my pictures. But you can make all of that work, right? And none of that requires big fancy calculators. This requires a little bit of good old-fashioned elbow grease and some geometrical intuition. Anyway, I'll go over the corner points method, which is a very much more concrete method, later this week in my next video. So if you don't like the non-concreteness of today's stuff, it's not the only thing we're going to be looking at. So I promise the numbers are coming close behind. I'll see you next time.